So up to this point, we've been building the periodic table and doing electron configurations and orbital diagrams from theory, from the quantum mechanical theory and what we know about how the quantum numbers work. That works really well, but remember how we had that funny little situation where we would have 4s and then 3D, or we'd have 5s and then 3D, and even more fun, 6s and then 4f, and then come back to 5D, right? Those were all kind of oddnesses that I just told you were true when we did Aufbau. What I want to build up is an experimental technique that showed us that this was true, and it's called photoelectron spectroscopy. So spectroscopy is a big deal in chemistry. It's the use of light to probe the inside of an atom or a molecule or a system, right? Light is how we look inside an atom or a molecule and figure out how it works. And so this thing is basically a graph. And we'll talk about how those work going forward and how this is related to the electron configurations that we already know how to do. First, let's look at the experiment. What I need you to know is that what happens in photoelectron spectroscopy is that you use a UV light or an X-ray light, depending on how strong of a source you need, how high of an energy. And what it does is it hits your sample, and that could be atoms or molecules. And that knocks electrons off of it. And the electrons go through an electrical potential that spreads them out by speed. The fastest ones come out first, the slowest ones come out second. A detector picks them up and then turns them into a graph, right? So electrons ejected from an atom or a molecule, right? That's the big deal about photoelectron spectroscopy. That's the first thing that happens. And then two, the kinetic energy of the electron relates to what orbital it came out of. Photoelectron spectroscopy helps me tell the difference between electrons that are in 1s and 2s and 2p and all that good stuff. Before we look at the photoelectron spectrum itself, though, I do want to divide our electrons into two different categories now. And to do that, I want to do the electron configuration for sodium. Sodium has 11 electrons. And so we'd say 1s, or 1s2, 2s2, 2p6, I'm up to 10 now, 3s1. And what I want you to notice is that everything with a 1 is totally filled. So this is a full shell. And 2s and 2p also represent a full shell. It represents going through a full row of the periodic table. So these electrons together are the ones that we call the core electrons, the inner electrons. This set on the outside are called the valence electrons. Similarly, let's go ahead and do fluorine. Fluorine has 9 electrons. 1s2, 2s2, 2p6, sorry, not 2p6, I can't add, 2p5, right? This is core because it's full. These are valence because it's not full. There's 1 valence electron here, there's 5 valence electrons here. So we just add up all of the electrons that are in the outer shells so that we can tell the difference. And the reason is that the valence electrons are the fun ones, right? These are the things that react. They're lost or gained if I go through chemical reactions. They form bonds, right? All of the interesting stuff happens at the valence electron level. Core electrons do absolutely nothing. They hang out and they're there to watch the show, but they get untouched. It's these valence electrons where the real interesting stuff is. So here's a photoelectron spectrum, or PES. And what I want you to understand is that an individual peak, so there's 1, 2, 3, 4, 5, 6, there's 7 peaks in here. Each peak represents an orbital. And lower energy peaks represent orbitals that are lower in energy. And remember that lower in energy means closer to the nucleus of the atom. So when we drew our thing here and we had 1s and 2s and so on and so forth, we're assuming that the nucleus is here and everything else is working its way out. So the ones on the left, we always start with 1s, and then we know alphabet, right? This is 2s and 2p and 3s and 3p and 4s and 3d. Which really means that I can now build this into an electron configuration. And I start comparing heights. I notice that all of these are the same height. So I'm going to assume that those are occupied. So I've got 1s2 and 2s2 and 3s2. Well, to get to 3s2, I have to have a completely full 2p. So it must be 1s2, 2s2, 3p6, or sorry, 2p6, 3s2, and these are the same height, so that must be 3p6. And now the fun happens. I know there's 4s, and then I know that 3d comes next because I know my alphabet. But you notice how these peaks are not the same height. So this is probably a 1. And then I notice that these peaks are not the same height. I know that the only thing that can happen is S1D5. There's no funny business like S1D6 or S1D2 or something. So I know that this is it. And I can use that to identify my element. Let's talk a bit more about these peak heights, right? So remember, this is argon, 3s2, 3p6. So here's my 1s and 2s, 2p, 3s, and 3p. And again, I see that these are all the same height, so I know they're completely full. And then I know that these two are the same height, so they must be the same number of electrons, right? The height is related to the number of electrons in the orbital. Now I look at sulfur, and here's where I can tell part of the difference. And now I return to my chromium from the other slide, right? We said 1s and 2s and 2p, 3s, 3p, 4s, 3d, right? Again, same height or same height. So they must be the same number of electrons, but these two are not the same height, so I know that they're different. I use the relative heights to get the relative numbers of electrons. Let's try a couple. Here's one photoelectron spectrum. So let's take a look at some of these for some more practice. Again, just work your way up, right? 1s, and it's full. 2s2, 2p6, 3s2, 3p6, 4s1. Where is that on the periodic table? Well, 1s2, 2s2, 2p6, 3s2, 3p6, 4p1 is potassium. So there's my identification. And if I wanted to make an orbital filling diagram, remember, I'd just make my lines 1s, 2s, 2p, 3s, 3p, 4s, and I'd fill them up. Just like that. Orbital diagram on the bottom, electron configuration on the top. Here's the last example where it gets slightly trickier. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now we know that the next thing is 3d, and since it's another peak beyond, it's probably a 10. Look at that. Looks to me like these are the same height, and we know this is 4p, so 4p1. Let's stop and look up what element that is.